Hello and welcome to this first lesson in Unit 13 of OCR A, A-level Physics, which is about quantum physics. So the technologies that you see on the screen right now are all dependent on the ideas from this topic, quantum physics. So computer microchips, the CPUs in your computer, in fact any integrated circuit, medical imaging techniques such as MRI scans, the way that TV screens work, and electron microscopes all depend on this quantum behavior at a small scale, which is quite counterintuitive ideas, some of them, but they certainly underpin these technologies which transformed the 20th and will continue to transform the 21st century. Later on in this course you'll learn in the medical imaging topic about how we can get this amazing amount of information non-invasively. Okay, so the first place to start with this then is something referred to as the photon model. We've done quite a lot of work on electromagnetic radiation so far, where we've considered EM radiation as a wave, and it certainly behaves in a wave-like manner. But in this lesson we're going to start to consider EM radiation as a particle, and the particles that we're talking about are referred to as photons, as Einstein called them, and we're going to look at that. We can find out the amount of energy that a photon has got. There's an equation that we need to know. In fact, it's the one that's on the screen now. And there are some new units for energy that we're going to be using as part of this topic, and Planck's constant is something else that we need to understand about. And there's at the end I'm going to show you a method for determining Planck's constant with quite simple apparatus. So if we go back to the 17th century and the work of Isaac Newton discovered a great deal of really important stuff. He did a lot of work on forces, for example, which his ideas from that were still in use when they were building the rockets to go to the moon in the 20th century. However, when Isaac Newton studied light, he came to the conclusion that it was a stream of particles which travel in a straight line with finite speed and possess impetus. And even 50 years after his death, those ideas were begun to be overturned. Thomas Young is a very important figure in this. We've already met his work, particularly the double slit experiment. What's interesting here is up until that experiment was done, light was considered as to be a stream of particles. And then after Young's experiment, because Young demonstrated that light behaves as a wave, the conclusion that was drawn was that light is just a wave, and so the particle nature of EM radiation was ignored at that point. Actually, it turns out that they were both right, and that the way that light behaves, it depends on the situation. Sometimes we can treat it as a wave, and sometimes we can treat it as a particle. So the particles that we're talking about are referred to as photons. So Max Planck, towards the end of the 19th century, discovered that electromagnetic energy could only exist in certain values. Unlike a wave, it doesn't have a continuously varying intensity. It has the energy comes in steps, and those steps or packets he referred to as quanta. And Einstein, quite soon after that, developed this idea further, and he referred to these little packets as photons. And the idea of the word photons has stuck from that, but we still also have the term from Max Planck, quanta, in the title of this area of physics, quantum physics. So that word quantum is meaning about packets. Packets of energy is actually what we're talking about here. So it turns out that the EM radiation, including light of course, behaves both as a particle and as a wave. And sometimes we apply the particle model, particularly when electromagnetic waves interact with matter, and at other times the wave model is applied. For example, explaining how EM radiation travels through the empty vacuum of space. Both models have their applicability. They've both been tested. They both stand. It's just that they different model applies in different situations. Right, back to Max Planck. What he discovered was that an individual photon carries a certain amount of energy, this quantum of energy, and that amount of energy is proportional to the frequency of the radiation. E is proportional to F. Now, if we want to turn a proportionality into an equation, we need a constant in there, constant of proportionality. In this case, it's referred to as H, and that was named after Max Planck, so it's called Planck's constant. It's been measured, and I'll demonstrate a little while later how that can be done with quite simple equipment nowadays, actually. E equals H times F, and Planck's constant has a value, as you can see on the screen there. It's very small, 10 to the minus 34. The units there of Planck's constant is joule seconds. Just think about that for the moment. E is energy, so that's obviously in joules, isn't it? Frequency is hertz, and hertz can be expressed as per second, waves per second, so that's 1 over seconds, seconds minus 1. So in order to get joules out as the units of energy, then Planck's constant must have the units of joule seconds, because when you multiply joule seconds by 1 over seconds, the seconds all cancel out and you end up with just joules. So we can relate this equation that we've just had, E equals hf, to the wave equation, where the speed of an electromagnetic wave is related to its frequency and its wavelength. So substituting into E equals hf for frequency, we get E equals hc over lambda. Now this is a really interesting equation because it's got terms which have wave properties and terms which refer to particles. So E is relating to the energy of photons. So photons, that's a particulate behavior, but it's also talking about wave properties, the wavelength. So this equation links particle behavior of EM radiation with the wave behavior of radiation. And it also shows us that the energy of a photon is equal to, or rather proportional to 1 over the wavelength. So EM radiation with the longest wavelength has got the lowest energy, so radio waves, for example, whereas a short wavelength, high frequency EM radiation has got the highest energy. And we've already learnt that X-rays, gamma rays are the most damaging. We refer to those two and UV as ionizing radiation because the photons carry enough energy to ionize atoms, which in case of living tissue is very damaging. Okay, so here's a worked example of how we could apply this equation. So if we have a laser light with a wavelength of 633 nanometers, just turn my pen on. If we want to work out the energy of the photons in this beam of red light, the first step in any calculation like this is to identify the correct equation. Remember, this will be on your equation sheet in the exam. E equals hf. So h, remember, is Planck's constant, and that is also shown in your equation sheet. But we are told the wavelength, but we need f in this equation, so we need to do what I showed you in the previous screen. We need to substitute for f using this equation here, so that E equals hc over lambda. So we know the wavelength of the wave, it tells us that in the question. We can look up Planck's constant. C is the speed of light. We can also look that up on our equation sheet. So we do our Planck's constant, 6.63 times 10 to the minus 34, times C, which is 3 times 10 to the 8. The only thing we need to be cautious about is this wavelength is given in nanometers. So nano refers to something being 10 to the minus 9. So 633 nanometers is 633 times 10 to the minus 9. I know that's not in standard form, but that's the easiest way of plugging it in. Your calculator will cope with that, I'm sure. And that gives us the value of the energy of a single photon, 3.14 times 10 to the minus 19 joules. So you can see an individual photon carries a tiny amount of energy. And in fact, we need perhaps a different way of talking about the energy when we're at this scale. Joules not terribly useful because we're talking about a tiny number of joules here. So let's think about the things at a subatomic scale, and we want something that is a bit more convenient. And the unit that we end up with is something called the electron volt. And the electron volt is the amount of energy transferred to an electron when it moves through a potential difference of 1 volt. So imagine these two blue lines represent two metal plates, and the metal plates have a potential difference of 1 volt. So this is 0 and this is plus 1 volt potential difference. So because this electron has a negative charge, it will be attracted to this plate. So the energy transferred, the work done, if you like, in lifting, as it were, this electron from here to here, okay, that's the force times the distance. Well, you can think of the distance as being this potential difference here, and the force being the charge on the electron. Okay, so to put it another way, we know from the work that we did in chapter 9, it was that the amount of the energy is the potential difference multiplied by the charge. So that's the V for the potential difference times E, which is the charge on the electron. So the work done, the energy transferred is 1 volt multiplied by the charge on the electron, 1.6 times 10 to the minus 19 coulombs. So 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules, if I can get my words out. And obviously we need to go back the other way too, so we want to better convert joules into EV. So we multiply by 1 over 1.6 times 10 to the minus 19, which means that 1 joule is 6.25 times 10 to the 18 EV. So a lot of electron volts needed for 1 joule. Okay, so sometimes when we're dealing with very large numbers of EV, we'll use prefixes. So we might use kilo EV, we might use mega EV, or we might use giga EV. These are prefixes that you need to know. They come out of module 2. So generally speaking, a capital letter is a multiplier. Kilo is an exception, that's always a lowercase k. So kilo is multiplying by 10 to the 3, mega is multiplying by 10 to the 6, and giga is multiplying by 10 to the 9. So we can see from this chart here, we've got photons of different electromagnetic waves in the spectrum, starting at the top with radio waves, which have the longest wavelength. They have a wavelength somewhere in the region of 3 meters, which means they've got a long wavelength. That means they've got a low frequency. That means they've got a low energy. So radio waves carry 6 times 10 to the minus 27 joules per photon, or 4 times 10 to the minus 8 EV. They haven't even got much energy in terms of EV. If we go to the other end of the spectrum, to the gamma rays, they've got the shortest wavelength, so the peaks are very close together. They've got a high frequency, and that also means they've got a high energy. So typical energy of a gamma, the photon of a gamma wave is 1.5 times 10 to the 6. So that would be 1.5 mega EV. Okay, so we can use this information actually to make some calculations of Planck's constant. I mentioned earlier that it's been experimentally determined. Well, you could do it with equipment like this. So we would use an LED, a light emitting diode, and that's this component here. A diode is an electrical component which forces electricity to flow in one direction only, and a light emitting diode is one which lights up when it's allowing the current to flow. So in this circuit here we've got a voltmeter across it measuring the potential difference across the LED, and we've got a potential divider here which allows us to vary the PD across the LED so we can find out what happens. What we find is that they have a threshold voltage. Below a certain voltage they don't light up. As you increase that PD, you get to a certain point when they suddenly light up. So we call that a threshold PD. And then the LED begins emitting photons of a specific wavelength. In other words, LEDs have a certain colour. So you get red ones, green ones, yellow ones, blue ones. Each LED of a different colour has a different threshold PD. So the photons of light that are being given out by those LEDs have got different amounts of energy depending on their colour. So a blue LED is emitting photons of a shorter wavelength, and therefore they have a higher energy, whereas the red LEDs are emitting EM waves of a longer wavelength, so their photons will have less energy. Right, so here's what you could do. So if you were to apply a negative potential difference to the LED, you can see we get no current. For a negative PD, always zero current, because an LED, like any diode, only allows current flow in one direction. If we apply a small positive potential difference, then we get still no current. And if we gradually increase that current, we get to a certain value here where we reach a threshold and the LED starts to light up. And if we're measuring the amount of current that's flowing, and we can see that as we increase the potential difference, the current also increase. But if we just stick back to that threshold, we're providing just enough potential difference for the LED to light up. So that means that the energy that we're providing, that we're transferring in the circuit, is equal to the charge on the electron multiplied by that potential difference. So that is giving us the amount of energy that we're supplying. But of course, that energy is pretty much the same as the energy of the photon that's being emitted. I said pretty much there. We'll come back to this idea in a lesson or two's time. But what we can say is if we're just at that threshold, then the energy that we're putting in is producing these photons which have this amount of energy. So if we know the wavelength of the light emitted by the LED, and by extension we also would then know the frequency, and if we know the energy too, we can use that to calculate Planck's constant. So if we express that in terms of wavelength of the emitted photon instead of frequency, we get EV equals hc over lambda. So c is a constant, so we can use that to work out h. However, we can do it more accurately if we use a series of LEDs. Instead of doing this once, we'll do this several times. We want to know this threshold voltage, but we want to use several different LEDs to be able to calculate a more accurate value. So here's what we do, is we use different color LEDs. So that means that the wavelength of the light that they give out is different, and we measure their threshold voltage, the potential difference required just to make them light up. So they obviously need to be different types of LED. Each color has got its own threshold potential difference. So I want you to remember that the gradient is the answer. We should try in physics to plot our results in such a way as the gradient tells us something useful, because what we've got here is a series of points, and by plotting the gradient of the line of best fit, essentially we're calculating an average, and by doing this we're removing quite a bit of the random error in our measurements. So The formula of a straight line, remember, is y equals mx plus c. So if we look at this equation here, this is our y. So we're plotting v, the potential difference, the threshold potential difference on the y-axis, equals mx plus c. Well, if c, the intercept, is 0, look, it's going through the origin. Okay, so if on x we plot 1 over lambda, which we have done, the gradient of that line is hc over e. Well, if we know the charge on an electron and we know the speed of light, we can use that to calculate Planck's constant, which is h, by a little bit of rearrangement. Okay, so in this first lesson on quantum physics, we've introduced the idea that light can behave as a stream of particles, and that those particles are called photons, that photons carry a certain amount of energy, and the energy in a photon is proportional to the frequency of that photon, and we can relate the energy by using Planck's constant, E equals hf, and by using the wave equation we can relate the wavelength to the energy as well. In the next lessons we're going to go and look at some more rather counterintuitive ideas about how electrons behave when they're subjected to photons of different wavelengths of EM radiation. I hope you found this useful. Leave a comment below if you want to, and see you in the next lesson. Bye.